So this is the chi-square test of independence or test of association. As we saw in the past, when we're engaging in social research, we have a lot of questions about how groups differ from one another, right? We had the example of how liberals and conservatives differ in their child rearing practices. We had questions about how certain methods for recall actually improve recall. But those were centered around comparing two groups in terms of one outcome. And specifically, we were looking at how does the mean of one group relate to the mean of another group, or third group, fourth group, nth group. Right? Sometimes, rather than comparing the means, we want to know about the distribution, right? Specifically, how do categories or attributes of one variable line up with categories or attributes of another variable? Not specifically that one group is going to have a higher mean than the other, but like, how do they flow together, right? And that gets us to this larger question of how do these two variables in general relate to one another? Right? We might want to know, are Black individuals more likely to be Democrats? Or we might want to know more generally, how do racial ethnic categories line up with political affiliation? Are racial ethnic categories associated with political affiliation, political party affiliation? Here we might look at the comparison between white individuals and Black individuals. That would be our race and ethnicity category. You'll notice we have two groups within the white and Black. And we want to see how that compares to another variable, political party affiliation. Here we might want to compare the liberal or Democrats to Republicans. Importantly, when we're looking at how these things are distributed across categories, we're not confined to a specific number of categories. So we saw with the t-test, we're looking at means as the main outcome of interest, but we could only look at two means at a time, right? When we compare it, group 1 to group 2. We extended that with the ANOVA. We said, hey, sometimes we don't have just two groups. Sometimes we have 3 or more groups. So we want to answer these kinds of questions in terms of a mean outcome. Now we're saying, well, maybe we're not concerned with just having two groups. Maybe you want 15 groups or n number of groups, but we're not also concerned about means as the outcome. We just want to see how these various numbers of groupings relate to one another. So here's another example. If you want to compare cities, suburbs, and rural areas, do cities experience more robberies? So we're looking at cities compared to suburban areas compared to rural areas. If we want to see, does one of these groups have more or less robberies? We're not only interested in robberies, we're interested in robberies in relation to what? So we can think of robberies as one type or one category within part 1 crime, right? So you might have the relationship between location type, like city versus rural versus suburban, and then you can compare that to different types of crime. So do cities have more or less of one of these 8 types of crime? Do suburban areas have one or more of these 8 types of crime? And the same thing for rural areas. And then are liberals or conservatives more permissive in their child rearing? We used this research question in a t-test before, right? We looked at liberals and conservatives, and we wanted to say, have they differ in their mean permissiveness? So we have a score for permissiveness for both of these groups, and we want to see, does one group have a higher score than the other? Let's say we wanted to answer that question in a relational way. And by relational here, I'm looking at just relationships between variables, right? Is permissiveness related to these categories? Well, then we have to start thinking, instead of means, we need to think of permissiveness as a category. So we can use that same kind of question to dummy down that outcome variable to something like permissive or not. So we can see if being either liberal or conservative lines up with being either permissive or not. So now we're no longer continuous, we're no longer integral ratio, we're category. The key across all of these is that we're looking at relationships between two nominal or ordinal variables. The chi-square test is one of these inferential statistical techniques, right? We're trying to infer to the larger population about what's going on, given the data from our sample. Inferential statistical technique to test for relationships between nominal or ordinal variables. More appropriately, it tests the statistical independence of these two variables, the absence of an association. So this is why it's called the test of independence or test of association. If we recall, the null hypothesis for the t-test was that there was no difference between these groups, right? So group A and group B, group 1 and group 2, there was no difference in the means. ANOVA, null hypothesis was there's no difference in the means between group 1 and group 2 and group 3 and group N. With the chi-square, we're testing independence or the absence of an association. So it's similar to a lot of these other tests. No difference meaning zero. With statistical independence, we're testing the absence of a relationship, the absence of an association, right? These two variables are not related to one another in the population. So we're basically just calling this test the chi-square test of the null hypothesis. So everything we're doing is testing a null hypothesis. Again, when we were looking at T and ANOVA, we were looking at mean differences. The means don't differ. Here, we're no longer looking at means. We're just saying, is there a relationship? Is there an association? Importantly, the chi-square is based on a crosstab that helps us visualize bivariate relationships, especially when there are smaller numbers of categories within these bivariate relationships. You might think of a table with one variable on the left-hand side on the rows, one variable on the columns, and you can see within each cell in this table, it's going to give you a breakdown of how many people fall into one category of one variable and one category of another variable. So you can think of it as you have categories of a variable on the columns and categories of a variable on the rows. So you're seeing how, for instance, if we used our example of Black individuals being Democrats, you say, okay, what other categories exist that are political party affiliation variable? Well, let's say we only have Republicans and Democrats. So on the columns, you'd have Republicans and Democrats. On the rows, you'd have various categories of racial ethnic breakdown. So let's say we only had Black and white. So within each cell, you would have Black Democrats, Black Republicans, and then you have white Democrats and white Republicans. So you can break down every relationship in that same way, 2x2 table or 3 by however many table. Right? So this crosstab just helps us visualize where are the observations lining up in relation to one another. Allows us to more appropriately compare the distribution of the categories of one variable across categories of another. And what we're really looking for is how numbers of cases are distributed across each of these categories. Are most of these people identifying as Black and Democrats? If we saw a relationship like that, we'd see maybe 100 people who identify as Black Democrats, one who identifies as a Black Republican, one as a white Democrat, one as a white Republican, right? So here we would see a relationship where most people are not only identifying as Democrats or Black Democrats, but you have mostly Black individuals in this sample and mostly Democrats in this sample. So you can see that visually when you look at one of these cross tabulations. So for instance, using our earlier example of political orientation and child rearing method. So up here, we see the variable political orientation. On the rows, we see child rearing method. And what you do is you break down the categories of each of these variables. Here, we see there are 15 liberals who are permissive in their child rearing technique, 10 conservatives who are permissive, 10 conservatives who are not, 5 liberals who are not. What can we learn from this table? Does it seem like there's a relationship? What is it telling us? Let's think about the breakdown of liberals versus conservatives. Are there equal amounts of liberals and conservatives in this sample? Yeah, we see that in the column here, we see here's a total, and the totals are based on the rows. Here in this row, we see total, and it's based on the column. So if we look, we see a total of 20 people who identify as liberal, 20 people who identify as conservative. Perfect, right? So we can see a breakdown that way. If we look on the rows, we see that most people tended to identify as permissive, right? They were permissive in their child rearing method. More importantly, we'll see there's an even split for conservatives, right? They were equally as likely to be permissive as not. Of those 20, 10 identified as permissive, 10 identified as not permissive. But when we look to the liberal category, we see that most of the liberal individuals tended to be permissive. This might suggest that there's a relationship between political orientation and permissiveness, such that liberals tend to be more permissive than conservatives. But we don't know that yet. So how do we identify that? Well, we have to go through a chi-square test to determine how extreme of a difference this 15 or this 10 or this 5 or this 10 is from what would be expected by the null hypothesis. That sounds a lot similar to what we did for t-test and ANOVA. How different is this from what is expected under the null hypothesis? The chi-square test takes into account frequencies in this crosstab across these categories, and it tests the absence of the association. So the chi-square test is something that is applied to a cross tabulation. The null hypothesis is that there is no relationship or no association between these two variables in the population. Therefore, we can say that these variables would be statistically independent. And then the research hypothesis or alternative hypothesis is that there is a relationship between these two variables in the population. So if we take our example of political orientation and child rearing, the null hypothesis would be something to the effect of there's no association between political orientation and child rearing in the population. The variables are independent of one another. In the population, we would expect that political orientation should not be able to predict or explain or be related to one's child rearing method. Another way of saying it is that the frequencies of liberals who are permissive does not differ from the frequency of conservatives who are permissive. Or more generally, the frequencies of that dependent variable, child rearing permissiveness, are expected to be the same across all of these categories, or similar across these categories, right? So the null hypothesis is just saying, I would expect no difference. If we randomly shuffled the data, we should expect similar frequencies across all of these categories, given the number of people in each grouping. If we had 100 people total and most of them identified as Democrat, it's a little bit harder. We can't just randomly shuffle and say everybody's going to be evenly distributed. So given the data, we would expect an even or similar distribution across these categories of the dependent variable. And the research hypothesis says that these two differ. The frequency on the outcome variable of the predictor variable differs. So the frequency of liberals who are permissive differs from the frequency of conservatives who are permissive. But as we recall from our t-test and our ANOVA, we don't know. We said the mean of this group differs from the mean of that group. But then we're like, okay, well, is 1 point enough of a difference? Is 2 points? Is 3 points? Is 4 points? Is 50 points? What counts as an extreme enough difference? So we take that same logic that we use in the t-test to think about the extremeness of that difference and apply it to this logic of relationships between categories or frequencies within each category. So how do we do that? Well, we have these things called observed and expected frequencies. Observed frequencies are just that, the things that are in the table. So if you hand me a table and we looked at that breakdown of liberals versus conservatives and permissiveness, we had 40 people total, 20 liberals, 20 conservatives. We had 15 liberals who were permissive, 10 conservatives who were permissive. The observed frequencies are the counts that are actually observed from the data. They exist in the bivariate table. The expected frequencies, however, are what we would expect the cells to look like if the null hypothesis were true. Well, how do we know what the expected frequency should be if the null hypothesis is true? Luckily, we can count on calculations of the margins of a crosstab to give us some indication of what we would expect in each cell. What do? Let's say we took some data on sex broken down by a student's first gen status. So this is from an incoming freshman class. And there are 4,600 students here. How do we know? Well, we can go to the total cell. So we have those who identify as men, those who identify as women, and we see there are 691 men who identify as first generation, 1,245 women who identify as first generation. So similar question as the last crosstab we saw. What can we glean from this table? When you compare women versus men, we see women tended to identify more as first generation than did men. But then the same could be said for the men category too, which is the case if we just look at this total column. Most people or more people tended to identify as non-first generation than first generation. So good, we're getting everything we need from this table. This is perfect. It becomes much more difficult when you have a lot more categories within a variable. So let's say we were truly including a plethora of sex, gender identities here. And instead of just first generation, non-first generation, let's say we broke it down by like racial category. There'd be a lot of different cells here. Some of the cells would have 0 people. Some other ones would have hundreds of people. So that's important to keep in mind. It becomes so difficult to start figuring out, okay, what is the relationship here when I have 15 categories of one and 10 categories of another? That's to say, this is a nice visual representation for us, but it typically only works with smaller tables. So now we need to ask, if we're really trying to see, is there a difference between what is expected and what is observed? This is what is observed. What would happen to the cells if the null hypothesis were true? What would those cells look like if the null were true? The data are the data. We can't assume that it's abiding by the null hypothesis, but we can figure out what they would look like given that there are 4,600 cases. We can take that information and say, If the null were true, we should be able to evenly split these or split these in some way that looks like nothing's going on. So we can create a table of expected frequencies given the null hypothesis, or the table about what it would look like if there was no association between these categories. So how do we do that? Well, we remove the actual data, and by the actual data, I mean the cell counts that are important for us, not the totals, not the total, but the actual cells. Men who identifies first, men as non-first, women as first, women as non-first, remove all of those. And then we're gonna fill in the table with numbers that would be expected given a true null hypothesis. We have this cool calculation to figure out what a breakdown would look like if the null were true. So we take a row marginal and a column marginal, and we divide by the total number of cases. So we create a calculation that is based on men who identify as first generation. We create a calculation of the number of cases that should exist and divide it by, or take an average of that number, divided by the total number of cases. And that gives us a frequency that should be expected in this cell. So for instance, if we were looking at men who identify as non-first generation, we know in total there are 1,950 men, people who identify as men in this data set. We also know that there are 2,684 non-first generation individuals. So we can use that information to calculate a reasonable estimate of what should be expected in that cell. We take 1950, multiply it by the row marginal, 2684 for that category, and divide by our total here. So that's what goes into the calculation for chi-square. Take column times row over the number of cases, and then you can fill out this whole table. So you can do that for each case. So let's say we wanted to fill in this cell, first generation individuals who identify as women. This is what the table would look like if we filled it in with those calculations. So these are quote unquote expected frequencies given a true null hypothesis. If the null were true, we should expect that the breakdown between 1950 men broken down by non-first generation status should be equally distributed based on the number of cases that are total in the total column. Right? So that would leave us with an expected value of 1551. Obviously, these are whole people, so the 0.14 doesn't really make much sense. But again, it is an expected of what is expected by the null hypothesis. So that is what is expected. This is what the table would look like if it were the expected or the null hypothesis state. So now what we do is we take that information and we compare the actual data to the expected data. So what we can do is look at this actual versus expected men first. And we see actual was 691, expected was 817. So what we actually got in this table was smaller than what was expected by the null hypothesis. Here, what we actually got for women first was higher than what we expected, right? So lower for men first, but higher for women first, right? And you can go through and see ours is lower actual than expected, ours is higher actual than expected. So what we do next is take that information and implement the chi-square test, which looks at the differences between actual cell counts and expected cell counts. And then we can sum up all of those differences and see how different is that from what is expected by the null. And we would expect that low differences would mean that it's not that different from the null hypothesis. Differences of 0 between the actual and the observed would mean that those counts in the actual cells are very close to the expected counts, very close to what is expected by the null. So essentially what we would want is, after summing up all these differences, we want a large number. A large number would indicate there's a lot of differences between the actual data and the expected data, therefore lending support for our hypothesis that one group related to categories of another group. So the chi-square test, again, examines whether or not two nominal or ordinal variables are independent of one another, examines how the frequencies within categories of one variable are distributed along categories of another variable, measures the size of the difference between observed and expected frequencies. Again, very similar to the t-test and ANOVA, looking at the size of that difference. We calculate the difference for each cell. Again, you should know this by now after a couple of weeks and doing the bivariate association check. Chi-square test looks at two variables. It's a bivariate test, and both of those variables are nominal or ordinal. Here in the chi-square test, it uses that same logic, but applies it to expected versus observed frequencies. So the null hypothesis for the chi-square test of independence is that there is no difference. There's an association between these two variables, but specifically, when you get into the calculations, it's really looking at, is there a difference between the observed and the expected, or is there not a difference? So the null here, if we take it that step further, it's that there's no difference between the observed and expected frequencies for these categories of the variable. The variables, therefore, are independent of one another. There is no association, no relationship between these variables. So we're just adding on the piece that not only is there no association, but specifically the observed and the expected frequencies do not differ. So the expected frequency is equal to the observed frequency. The research hypothesis just says that there is a difference between observed and expected, that there is an association. We need to figure out what counts as a difference. 0 is obviously no different. But is 1 large enough a difference? 2, 3, 15, 37? What is large enough, or what is extreme enough of a difference? The assumptions of the chi-square test, there are only 2. Independence of observations, that sounds familiar. These groups aren't related to one another in the sense that observations in each of these groupings aren't tied together. So a good way around that, as we mentioned before, is to do randomly sampling observation from a given population. And then secondly, normality of a distribution. The problem with this assumption of normality is that every time we try to assess normality, we're looking at plotting, right? We look at the visualization, right? We plot the means of some variable broken out by categories of another variable. We plot the histogram. We look at the box plot. We look at the QQ plot. But those are all necessarily based on interval ratio outcome variables. Here in the chi-square test, we don't have an interval ratio variable, predictor or outcome. So how do we tell if the data are normally distributed? Well, if you refer to your Howell textbook, one way of determining if the distribution is relatively normal is if 20% or more of your cells are not below 5 cases. So if you have more than 20% of your cases have expected cell frequencies below 5, you need to check, okay, are most of them coming below 5? Or is it just 1 cell out of 30 cells that are coming below 5? So we don't want more than 20% of our expected frequencies below 5. And what that means, if you think about it logically, think about cases where you have 10 different attributes within one variable. Let's say you're going to use race ethnicity as a variable, and you use every possible category under the sun. Chances are, if you use every possible category under the sun, there are going to be people who don't exist in one of those categories, one or more of those categories. And if you try to create a crosstab with a bunch of zeros in it, it's not going to account for those zeros when we're trying to calculate these expected frequencies. You don't want cells with missing data or the possibility of that. A way to fix it is to collapse those categories. So instead of having 10 or 15 categories, maybe having 5 categories within a variable. That way it allows for clustering of cases. We want large samples. If you're going to have a variable with 15 categories in it, you want enough cases to allow for the possibility of enough people falling into each one of those categories. If you only have 20 people in your sample and you have 15 different cells, not everybody's going to belong in a cell. Much like the t-test, much like ANOVA, the f-test, the chi-square distribution has multiple curves. The interesting thing about the chi-square test is, like the ANOVA test, it's never quite going to be a normal distribution. The chi-square test is a one-sided test, just like ANOVA. So you'll notice that there are characteristics of the t-test here, there are characteristics of the ANOVA test here, but it's a one-sided test. Our chi-square value is going to range from 0 to infinity. So much like the 2 previous tests, the t-test and the ANOVA, we want to know if the overall difference between the observed and the expected frequencies is extreme enough. And if it is extreme enough, extremely different from what is expected by the null hypothesis, which is a difference of 0. If it is extreme enough, then we can, 1, reject the null hypothesis, 2, claim that we have a statistically significant relationship or statistically significant association between these 2 variables, which would mean that the association between these 2 variables exists in the population. Again, we're trying to infer from our data here about what's going on in the population. But again, what counts as extreme enough? Well, how do we find what's extreme enough? We see this distribution here on the right-hand side. We can probably guess that with each one of these curves, it's going to be based on sample size, or what we know as degrees of freedom. Each curve, because it differs, it also means that we're probably comparing our difference, our extreme difference, to some critical value. And we want to see, just like all the other tests, we want to see if our value, our observed value, our calculated value, obtained value is much greater than or less than that critical value. That same logic cuts through all of these tests. How do we figure that out? The logic here is that if our obtained chi-square value, to see if it's statistically significant, we have to compare it to a critical value. To find that critical value, we need, in the t-test, we needed degrees of freedom and our alpha level. With ANOVA, we needed our alpha level in degrees of freedom for between and within. Here, same exact thing. We need degrees of freedom and our alpha level. If I don't mention the alpha level, it's always going to be 0.05. Degrees of freedom. I mentioned before, degrees of freedom, because we're estimating information from a sample to a population parameter, we can count on a certain number of cases to estimate a mean for a population parameter, for instance. The same logic applies here. We're using a crosstab to estimate what that crosstab would look like in the population. Same thing as if we know the sample mean, all of that information, we can randomly select any numbers that exist in the world, but then it would necessarily predict the final number in that calculation. This is why we use that calculation of n-1. That same logic goes into the calculation of the crosstab's degrees of freedom, n-1. To calculate the degrees of freedom for a chi-square test, degrees of freedom would be the number of rows minus 1 times or multiplied by the number of categories in the second variable minus 1. So rows minus 1 times C minus 1. Much like everything else, if we're going to compare our calculated chi-square value to the critical chi-square value in the table. If our obtained is greater than or equal to our critical, then we reject. If our obtained is less than our critical, then we fail to reject. So again, same as everything else. Here, we could easily look at the chi-square table. Here we have alpha level of 0.99, 0.99, 0.975. I don't know who would want these alpha levels, but we're going with an alpha level of 0.05. So this is going to be the column we use, and then we just select our critical value based on our degrees of freedom. And we use that in the calculation of chi-square. So to figure out if there's a large enough difference between our observed and our expected frequencies, we do the calculation of the observed count minus the expected count squared, standardized by what should be expected. So how many standardized steps or how many expected steps is this difference? You'll notice that we standardize often by like variation within. Here, it's standardizing by the null hypothesis expectation. Given the null hypothesis, this is how many cases should exist in this cell. So given the null hypothesis, how many should exist in this cell, and how many of those instances is the observed away? How many steps away is the observed count? Basically, what we're doing is we're calculating this without the summation. We're calculating this part. Frequency observed over frequency expected squared over expected for each cell. And then we sum each of those different scores standardized, right? We have another example. So we had first generation men versus women. We had our observed frequency, our expected frequency from that table. Observed, expected for men first, same. So our observed table was 691, 1245, 1259, 1425. And then our expected were the other four. So what we're doing when we're calculating a chi-square is this. We're taking each table, men first generation, there were 691 in the observed table, and we're breaking that table out into different categories. We're saying here are the data from the expected counts. We're taking the frequency observed minus frequency expected. You'll notice you're going to find the same number exist across these categories, or similar numbers exist across these categories, right? The difference from what is expected. So what's going to happen when we sum all of these up? Much like we do for summing up different scores, it's going to be 0. So how do we solve for that? We square it. So we square these numbers, now they're huge numbers. And then much like we did for ANOVA, when we adjust that back down by dividing by mean square error, we adjust this number back down, this 1591, we adjust that back down based on the frequency expected in that cell. How many expected counts for the cell is this number? So this is the number that would go in each cell. For men who identify as first generation, we have this number of 19. Men who are non-first, 14. Same here, 14.22, 10.66. And our chi-square calculation is going to be the summation of all of these. So it's the sum of those numbers. So our chi-square value is going to be 57.99. And again, this chi-square number represents the difference between expected, or a quote unquote standardized difference between observed and expected. If this were truly no difference, this number should be close to 0. Here we got a number 57. That's huge, right? We're used to living in the world of 1.96, 2.58. Now we have something like 57. The value for chi-square ranges from 0 to infinity. So these numbers can get huge based on how big these numbers are. So the same as every other test, we compare the calculated 57 to a critical chi-square value. Again, if the obtained is larger than the critical, then we reject. We need to calculate our degrees of freedom. How many rows do we have in there? Well, we had 2 rows. We had first and non-first. We had 2 columns, men and women. So 2 rows minus 1 is 1. 2 columns, 2 minus 1 is 1. So 1 times 1 is 1, exactly. So we have 1 degree of freedom. That means that only one of those cells is allowed to vary or is expected to vary. So we can compare that information to our chi-square table item. So we have 1 degree of freedom, and we go over. So on the rows, we're going to have our degrees of freedom, 1 degree of freedom at the 0.05. So our critical value is 3.84. So our calculated value is 57.99. Our critical value is 3.84. So what does that mean? We reject the null. Our calculated value is much, 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 much larger than our critical value of 3.84. Therefore, we are way far out what is expected by the null. In the t-test, we had that center mark, and we try to run past the center mark. We move away from it, run towards the finish line, right? Same thing for ANOVA. We'd have the middle mark, which was no difference between these groups, and then we'd run past and see if we get more and more variation. We cross the finish line, and then we say we're in the rejection region. Here, we have that same thing, except the middle mark is 0, and we have a right-hand distribution. The finish line is at 3.84. We've surpassed it, and we're at 57.99. So not only have we surpassed it, we've exceeded what we would expect. So here we're in the rejection region, meaning we reject the null hypothesis, meaning that P, probability that the null of no difference between expected and observed is true, is less than our alpha of 0.05. Here, the chi-square obtained is in the rejection region, or if it's greater than our critical, then it's in the rejection region, we reject. P is less than alpha. It's a statistically significant difference from what is expected by the null hypothesis. So here's the example. To report the chi-square test, we say using the chi-square test of independence, I either reject or fail to reject the null hypothesis that there is no relationship between the first variable and the second variable in the population. Chi-square of blank degrees of freedom is equal to my chi-square obtained value, comma, my p-value. Is it greater than 0.05 or less than or equal to 0.05? So again, in our example, using a chi-square test of independence, I reject the null hypothesis that there's no difference between gender or sex and first generation status in the population. Chi-square of 1 degree of freedom is equal to 57.99. P is going to be less than 0.05. So if we wanted to calculate this for our other example, we have our marginal, our column marginal, our row marginal, total number of cases. We can calculate our expected frequencies. And usually when we're calculating expected frequencies, we can put them in parentheses next to the number just to show. So here we saw liberals who are permissive. We saw an observed frequency of 15, but expected of 12.5. We saw more observed than what was expected. So less here, or fewer here, and then more there. Take that information, calculate differences. So here's the same table up there. We say upper left, which is liberal permissive, upper right, conservative permissive, lower left, liberal not permissive, lower right, conservative not permissive. We sum them up at 0, so instead we square them, sum up all those squared numbers, then we do adjust based on the expected count for each cell. Right, so how many FE scores is this score? So it's 0.5 of those steps. So it's only 0.5 expected away from what is expected, right? So you can think of that as like how many standard deviation steps it is away. So 0.5, 0.5, 0.8, 0.8. We sum all those up, we get a chi-square value of 2.66. What does that mean? Is that big? Is it small? Small, yeah. A lot smaller than our last example of 57. What do we do next? Well, we take this obtained value and we compare it to a critical value. So if we want to figure out what the critical value is, we got to go to the back of the table. And to do that, we need our alpha and degrees of freedom. Degrees of freedom, easy to calculate. Look at our crosstab. There are 2 rows and 2 columns. So 2 minus 1 times 2 minus 1, which is 1 times 1. It's going to be 1. So, wow, that's familiar. We just did a calculation with the degrees of freedom of 1, alpha of 0.05. And the critical value for that was 3.84, right? So we compare chi-square obtained 2.66 to 3.84 critical, and we find that our obtained is not larger than our critical. Our obtained is smaller than our critical. So what that means is didn't quite get there. So it did not cross the finish line, did not cross the threshold. Therefore, it is not in the rejection region. Therefore, we do not reject the null hypothesis in this case. Right? It is not much different from what is expected by the null hypothesis. And finally, I have this example. Political orientation and views of BLM. So I have this example. On this page, we have a walkthrough of chi-square test. Again, recall that chi-square test is looking at an association between 2 variables, or relationship between 2 variables, trying to see if they're independent of one another. And rather, that independence is really testing what's going on in a cross-tabulation for the frequencies of those variables to see, is there a difference from what is expected by the null hypothesis, right? So we're looking at independence in relation to difference from expected. So here, I'm just going to open up the chi-square R script and copy that over. I suggest doing the same. Here we walk through the actual steps. Since I just have the most recent version of VanStats, I'm going to hashtag this out. That way it doesn't run. All right, so I'll highlight this. Load all of those, good, so everything's loaded. If you haven't gotten the most recent version, run that line to make sure it works, make sure you get that. It may prompt you to select whether or not you want to update various packages. Select option 3, which is none. Do not update any packages. All right, so I'm loaded there. The assumptions and diagnostics for chi-square. So the assumptions. First, I'm going to read the mtcars dataset into my environment. I have the object there, 31 observations, 11 variables. Okay, for the assumptions, independence of observations, right? We answered this last class and the class before that and the class before that. Really, independence of observations is dealing with whether or not there's a random sample of data, right? Is it representative of the population? And I said, okay, let's just assume that it is. So for these data, even though it's probably not the case and probably a bad data set to use with such few observations, I'm going to tell you that these 32 observations, these 32 vehicles were randomly sampled. Therefore, there's an independence of observation. So now we've met the first assumption, independence of observations. Normality. So we have to examine the crosstabs for the expected frequencies. And we want to see that the distributions are relatively normal, or rather, we want to see that the expected frequency counts, 20% of them don't fall below 5 cases, right? So we look at the expected frequency counts for a table and make sure that it doesn't fall below 5 cases. How do we do that? Well, we use this function. Hopefully it still works, fingers crossed. Wow, my video's off. I should probably turn that back on. Not that it matters since we're not, I didn't notice I can't see myself. Hopefully this still works. But what this function does, it's a function called tab within the VanStats package. It enables you to examine the expected frequencies. Unfortunately, to examine the expected frequencies beforehand, you would have to run an actual chi-square test, and then you would call the expected frequencies for it. So that's what, in the past, that's what I taught my students to do. Just run the chi-square test. Don't look at it, then tell me if the expected frequencies is there less than 5 in any of those cases, in 20% of those cases. So here we're going to be looking at, I think the example here is looking at, let's see what those data are. I forgot what VS is. Empty cars. VS is engine, so V-shaped engine or not, or straight. So here we're gonna examine the crosstab between a V-shaped versus not engine and a manual versus not engine, right? So let's use this function. Let's run it tab. And what you should get is within this, you should get 2 tables. You should get a table broken out by VS and AM. So there's 2 variables, and this is for the observed frequencies. And then under that, you should get the expected frequencies, right? Is that what you're getting? Yeah, okay, good. It's working, it's working, it's working. So here we have 12, let's see, VS 1 equals straight and 0 equals V-shaped. So this is a V-shaped engine with an automatic transmission. So V-shaped automatic, there are 12 observations. So 12 cars are V-shaped and have automatic. 7 cars are straight and automatic. 6 cars are V-shaped and manual. 7 cars are, what is that? Straight and manual, right? So what can we tell from this? Well, we know that we have, what is this? 14 straight line vehicles or straight shaped vehicles and 18 V-shaped. So more V-shaped than straight. And then here we have more automatic vehicles, right? 19 compared to 13. So what we really want to know is, are these evenly distributed? Well, the only way to tell is by looking at what would be expected if they were evenly distributed, right? Right, because that's what the assumption is going into the expected frequency count, is if these numbers were evenly distributed, this is what it should look like. And what we're trying to see is that no more than 20% of these cells has fewer than 5 cases. So if we had a bunch of different cells, we'd have to figure out how much constitutes 20%. Here we have 4 cells, so the lowest we can go is 25%. And in each one of these, so we have 5.6, 7.3, 8.3, 10.68. So none of these cells have fewer than 5 cases. Therefore, we do not violate the assumption of normality. Right? So looking at this table, none of our cells fall below 5. So that's good. If one of these did fall below, then we would end up violating one of those assumptions. Why? Well, that would be 25% of the cases. I think there's a continuity correction that you can do if you violate that assumption, but I don't think I have that in the portfolio. I usually try to choose data that aren't going to violate these assumptions. And then next, run the chi-square test. Wow, that was difficult, bro. We're already at the chi-square test. Well, we checked the assumptions. We didn't violate any of the assumptions. Now we actually run the chi-square test to see, are these observed and expected frequencies different from one another? The function's called chi-square.test. And in there, we have the breaking down whether or not a car is V-shaped, broken out by whether or not a car is automatic or manual transmission. And here's where it is. The continuity correction is false, right? So because we didn't violate that assumption of normality, we don't have to make that correction. Right? If we did violate, we'd have to correct it, and that would change this call from false to true. So again, we didn't violate it, so we can run the chi-square test. I'm going to clear this window first, and I'll run it. Then we have Pearson's, just like Pearson's product moment correlation coefficient. Pearson, Pearson and Fisher show up a lot in frequentist statistics, by the way. Pearson's chi-square test, the data are drawn from the relationship between V-shaped engines and manual automatic transmission. X squared, which should just say chi-square or something like that. So the chi-square value is 0.906 or 0.91. So this means that our chi-square obtained value is 0.91. We saw our table, it's a 2x2 table, which means if we wanted to calculate degrees of freedom, it'd be 2 minus 1 times 2 minus 1, which is 1 times 1, which is 1, what we found here. We used this before, this degrees of freedom, with an alpha level of 0.05. We looked at that table and found that our critical value for chi-square was 3.84. So knowing that, we compare our chi-square obtained of 0.9 to 3.84. And we find that our chi-square obtained is not larger than 3.84, our critical value. So what that means is, if we're thinking about that distribution, we have 0, which is no difference or null hypothesis, no difference between expected and observed. 3.84, which is the finish line representing a true difference as expected from the research hypothesis. And then we have 0.09 or 0.9, which is barely past the starting point. We didn't leave the starting line really. There's no way we're close to the finish line. So given that we haven't crossed that finish line, that means we're not in the rejection region, meaning we don't reject the null hypothesis, meaning that P is not less than 0.05, or rather P is greater than 0.05. And actually we do see that here. The P value is 0.34, which is greater than 0.05, right? So here, all of that is to say that we can work our way backwards and say that P is greater than 0.05. That means it's not a statistically significant relationship between these two variables, meaning we're not in the rejection region, meaning we don't reject the null hypothesis, or we fail to reject the null hypothesis. So using all of that information, we can write it up down here. Using the chi-square test of independence, I fail to reject the null hypothesis that there is no association between the shape of the transmission of cars, comma, in the population. Chi-square with 1 degree of freedom is equal to 0.90688. P is greater than 0.05. There you could also report P is equal to 0.3409. I would accept either. But again, remember, like I said before, we're comparing to that standard of 0.05. So are we greater or are we less than or equal to? And there you have it.